One, how to define an acid and a base, okay? We said acids are proton donors, bases are proton acceptors. And then we looked at chemical reactions and we said, which one's the acid, which one's the base? We practiced identifying those, okay? Defining and then defining and identifying them in a chemical reaction. 2, we looked at conjugates. This is CON, conjugates, okay? Acid-base conjugate pairs. And we looked at how the charge changes. We said because acids are giving away a hydrogen ion, the conjugate base decreases in charge, -1, or it decreases by 1. And a conjugate acid, so the base accepts the hydrogen ion, and so its charge, if it was neutral starting out, becomes like a +1. It increases by 1 when it becomes the conjugate acid. And then we looked at reactions and we identified those. And then 3, we started talking about acid, base, strength. Okay. And that's where we finished. So we're going to pick up with this. We said we have strong acids and weak acids. And does anybody remember how we tell the difference between a strong and a weak acid? We said strong acids do what? Let me go back. Yeah. We were introducing this. We said strong acids will completely disassociate. Okay. So we're talking about the strong acid here. We used HCl as an example. We said it will completely disassociate. So we draw a single arrow pointing to the products to represent a complete dissociation. We get all products, we have no reactants left over. And we kind of walk through this by looking at if we had an initial concentration of, or an initial number of 100 molecules of our reactants, at the end of this, we're going to have none of our reactants, 0 of these, and we would have all 100 of our products, okay? Now, weak acids, we said they partially disassociate. So I'm going to write partial disassociation. So if we started out with 100 molecules of each of our reactants here, we'd have to do some digging. We actually have to calculate, well, how complete would this disassociation be? It could be, we'd have 40 molecules, 50, 60, 70, somewhere in the middle. Maybe a few would disassociate, maybe a lot would disassociate, depending on the strength of that weak acid, okay? Sometimes even just within the realm of weak, you have a spectrum. You have really, really weak acids, and then you have weak acids that are decently strong. They're just not strong acids, okay? We also need to understand that bases have relative strengths, okay? So strong bases have a high affinity for hydrogen ions, binds them really tightly. Example, that would be hydroxide is the strongest base we know. And weak bases have a low affinity for H+. Still binds H+, just not as strongly. So kind of the way we did on the previous slide, if we have a strong base, hydroxide, usually again, it's paired with some sort of group 1 or group 2 metal. So sodium hydroxide is the example here. If it reacts with water, we're going to draw a single arrow because we will have no reactants when this is done. What's going to happen is the OH, remember this splits up into Na plus and OH minus, and it's the lone pairs. Remember, you got to have a lone pair to be a base. The lone pairs are going to grab off one of these hydrogens from water, and that's going to, kind of sounds redundant, but it's going to remake water. And then what's left over from water is OH minus, and we'll also have some sodium cations floating around. Okay, so we'll get all products. The weak base, a good example here is NH3. That nitrogen has the lone pair. That lone pair will accept a hydrogen from water, and this is going to be a double arrow because this is going to have an equilibrium, back and forth, back and forth. So what we'll have is ammonium ion, NH4+, that's the conjugate acid of our base, increase in charge by 1, and what's left over, or what's left over from water is OH minus. Okay. All right. So with acids and bases, we have strong and weak. Now here's a table from chapter 10, table 10.1 in your textbook. And it basically shows you lots and lots of acids, and it tells you if they're weak or if they're strong. And then it shows you their conjugate base on the right-hand side. And it shows these arrows, the red arrow pointing up and the blue arrow pointing down, which points towards the strong components of each side, towards the strong acids and down towards the strong base. So if you're looking at the left-hand side of this, here are your acids. And you do not have to memorize this. I will give you this table on your resources page for exam 4. So it'll be right there available on Blackboard. So you can always look and see, if I tell you you have acid, blah, 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 you can look at this table and say, is it strong or is it weak? Okay. You'll only see stuff on the exam off of like this table. And all these up here, if you notice these strong acids, we cannot write an equilibrium for those. It's all single arrows. And then it shows you their conjugate base on the right side. Okay. And remember, the strongest acids, guess what? They make the weakest bases. Their conjugate base is the weakest. So if you have a really strong acid, the conjugate base is the weakest. Okay. Now, vice versa, as you go down this table and you have the weak acids and the very weak acids, the conjugate base gets stronger and stronger and stronger. And the example down here at the bottom being water is the weakest acid. Okay. We don't even think of it as an acid. It just kind of does what it's told depending on who it's around. And its conjugate base is OH minus, which is the strongest base we know of. Okay. So as you go up the table on the left side, you get stronger. As you go down this table on the right side, you get stronger. So the acids are on the left, bases are on the right. All right, any questions there? All right. Now, because we can write the double arrow when we have a weak acid or a weak base, guess what? We can write an acid dissociation constant. We can essentially write an equilibrium expression. Because the dissociation of a weak acid is an equilibrium, we can write an equilibrium expression. And I'll let you pick which emoji represents you, how you feel about equilibrium. I'm sure most of you will pick this one, and very few of you will pick that one. Okay, do you guys remember equilibrium? Our old friend equilibrium K, equilibrium constant. So let's write one for this expression right here. We've got a weak acid, which is right here, HA, and it's going to react with water and give us these two products, hydronium and the conjugate base. So this one is the conjugate base. And remember, K is equal to concentration of products over the concentration of reactants. And if you have coefficients, you plug those in as the exponents. Here we just have coefficients of 1 everywhere, so we don't have to plug in any exponents. But if you had a coefficient of a 2 or a 3 in front of any of your reactants or products, you plug that in as the exponent for the concentration of that thing. So our products here, K for the weak acid would be the concentration of the hydronium ion times the concentration of the conjugate base divided by the concentration of the weak acid times the concentration of water. All right, so this is a normal K, how we introduced it in chapter 7. We make some modifications for this though, and I'm going to walk you through this because if you remember, all acid-base reactions happen in water, okay? And we have water in this equation. So I'm going to read this down here. Even though water is a reactant, it is also the solvent. It is the solvent for this solution. So what that means is that the concentration, I'm going to turn this sideways so you can see better. Concentration of water is way, 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 way bigger than the concentration of any of the other reactants or products. It's just ginormous. So if we plugged in a value in where water is in a very large value, it would essentially give us a K of 0 every single time. If you divide by a hugely large number, you get a very, very small number. And so because we don't want K to just be destroyed by this large concentration of water, we just take it out of the equation, all right? I'm going to read this one though first before I get there. the concentration of water is not significantly affected when the acid disassociates because there's so much of it. So we're going to group water with K, and we're going to write a new acid dissociation constant. It's just for acids, just for weak acids. We call it Ka to kind of remind us, hey, this is not normal K. This is K for weak acids. So the way we do that, if I'm looking at this equation, if I just want to take water out and group it with K, I'm just going to multiply both sides by the concentration of H2O. And then it will cancel out over here. So essentially what we get after you make those edits is this down here. Ka equals K times concentration of water, which equals what's left over. Hydronium times conjugate base divided by weak acid, okay? Now, we don't actually just write this in. We just write Ka equals all of this stuff, all right? So you don't have to write this, but just so you know, that's what Ka is. Question though, why do we not write Ka for strong acids?
Because water is, does it have to do with water or no?
Anybody have another thought? Anybody else?
Everything disassociates.
What was that, Dakota?
If you have a strong acid, everything disassociates.
Yeah, you have a one arrow, remember? You don't have the double arrow for strong acids. You don't have that. Everything completely dissociates, so there's no equilibrium here. There's no reverse reaction. It's just a forward reaction only. No reverse. All right. So considering this Ka, I want to look at a few things. And I am going to post a problem. There's a problem on your chapter 10 homework. I think it's 10.66. I'm going to post a video of how to solve that problem on your homework. It is a problem about weak acids, and I think it has to do with pH. But before we get there, why is Ka useful for weak acids? The whole goal of today's lecture is for us to fully understand pH and what pH communicates and what it is and why it's important. And to understand that, we have to know about Ka, and then we're going to talk a whole lot about water. But why is Ka useful? Ka directly tells us about the strength of the acid, okay? The larger Ka is, the more product you have, okay? Because your products are on top in the mathematical sense, okay? So that's like saying this. If you have Ka equals 10 divided by 1 versus Ka equals 100 divided by 1. If 100 is on top, so that represents the amount of products you have. The more products you have, the larger Ka is, right? 10 divided by 1 is 10. 100 divided by 1 is 100. So the more product, the larger Ka is, the more products you have. And the product is the disassociated side. Those are the disassociated items. That's the side of the reaction that is how you see how the acid dissociated. So the larger Ka, the more the acid disassociated. And the more an acid disassociates, the stronger and more corrosive it is. Remember I said, would you rather drink, last week I posed the question, would you be willing to drink some HCl or some acetic acid? Acetic acid is a weaker acid. HCl is much stronger. It fully disassociates and it's way more corrosive. Because acetic acid is weaker, it's even safe for us to ingest. So what we're trying to say is the larger Ka, the stronger the acid. And I should insert, remember, we're only talking about weak acids here. The stronger the weak acid is. So we're kind of looking at a spectrum just within the weak acid portion or section of acids. All right, let's look at a table of Ka values. This is in your textbook too, and you'll have this on your resources page as well. Here's several different acids. And if we're considering what we just said about Ka, I want to know which one of these weak acids is the strongest and which one is the weakest. You can see all sorts, and they're all like with exponents here. That's because they're very, very small. So like this one, for example, 3.5, that would be 0.00035, right? These are all really small numbers. So which one of these is the strongest weak acid and which one is the weakest weak acid? What do y'all think? What do y'all think is the strongest? And I will say, this one just says large. This is actually a strong acid. Okay, so we won't consider H2SO4. Any guesses? Which one's the strongest? Remember we said the larger Ka, the stronger the weak acid. So which one has the largest Ka?
Would it be like the biggest negative, like HPO2 or HPO4 2 negative? Or would it be the
This one right here?
Yeah.
What do y'all think? So this one has the largest exponent.
I don't know.
But 10 to the
yeah, I don't know.
it's negative. So 10 to the minus 13 literally means this 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 2, 2. Sarah says HSO4, and I agree with her.
I agree.
1.2 times 10 to the minus 2. That is the strongest of the weak acids. On this table, I'll say. So that's like saying 0.012. Okay. So if you're comparing these two numbers right here, obviously this one's bigger. But Aubrey did point out the weakest weak acid. Which is the HPO4 minus, because its exponent is the smallest. So just because the number of the exponent is large, you have to bear in mind it's a negative number. So, and the further down, the larger your exponent is in the negative realm, the smaller the number it is, because that means the more the decimal place has moved to the left. Okay, questions there, or how to read this? All right. So if I, for example, a question, you're like, well, how could you even use this as a question? If I gave you like 3 or 4 of these acids and I listed them, I said, here's their Ka values. Could you rank them in order from strongest to weakest or weakest to strongest? Okay. List them in increasing or like increasing strength or decreasing strength. Okay. Something like that is a style of question I like to ask. All right, that's it for weak acids. And again, I'm going to post a video on how to work a style of weak acid problem regarding some pH stuff, but I don't want to post it until after we talk about pH. We're going to move on to kind of the, really, I think this is like the 4th big topic in chapter 10, water. Water is very unique. It's also very complex. And you didn't know how complex water was until before today, okay? Water can act as both an acid and a base. And you've actually seen this. We talked about this last week. We looked at 2 different equations. In fact, the 2 listed right down here. And we saw how water can act as an acid and a base. Water, again, it's just kind of like depending on what company it's in, whose company it's in, depends on whether it acts as an acid or a base. So water gets bossed around a lot, essentially. So if water's in the presence of a base, it's going to act like an acid. And what we're going to get here is It's going to give away the nitrogen on here is going to grab a hydrogen, and we've seen this several times now. Going to make ammonium ion, and you're going to have OH minus left over. There is the conjugate base. And if water is in the presence of this is a strong acid. And if you are unsure of what water is around, just go look at that table that says all the strong acids and all the weak acids and strong or bases and so on and so forth, and go see, is this a strong or a weak component? Is it an acid or a base? So here water is going to act like the base, and it's the lone pairs on the oxygen that are going to take this hydrogen from HCl, and we will make H3O plus, and we will make Cl minus, okay? And there is the conjugate base. So water can do both. And what's even a little more weird is water can act like an acid and a base with itself, okay? I like to compare this to people with multiple personality disorders, okay? That's a real thing. If you have that, just don't tell me. But it is a real thing, and water can do that. Water can, with itself, have different personalities here. One can be an acid and one can be a base. So what would that look like? What would it create? What products would we get here? If one molecule of water gives away a hydrogen and the other molecule of water accepts a hydrogen, what products do you create?
H3O and OH.
Yes, so hydronium and hydroxide. Okay, if you ever have twins one day, there's perfect names for a set of twins: hydronium and hydroxide. I'm kidding, that's terrible. H3O plus and OH minus. All right. So this actually happens in all acid-base reactions to a small extent because water is the solvent. And this just inherently happens because water just inherently does this. Now, it's not a ton, so you don't have large concentrations of these things, but you do have them present in every acid-base reaction. So it happens to some extent in all aqueous solutions. So they carry some concentration of H3O plus and OH minus. Now, because this is an equilibrium, we have an equilibrium here, a double arrow, we can write a K value just for water. This is pure, only for pure water. Okay, this is unique to pure water. So what is the expression for K here? It would be your products, hydronium and hydroxide, concentration of those divided by the concentration of water. And it's essentially like we have a coefficient of 2 in front of H2O if we just wrote 1 H2O. And so that's why we square that, the concentration of water on the bottom. And just like Ka, we're going to remove water. Okay, we're going to remove this from the equation because it's also the solvent. And we have very little, like I just said, of your products. This does not happen to a large extent. You mostly have reactants here. So your K is, guess what, going to be very, very, very small. So what happens when we remove water? We rewrite the equation and we call it Kw because it's specific to water. And if we just take water out of the equation, what we have left over is just H3O plus times the concentration of OH minus. Okay, so this is really a much simpler form of an equilibrium expression. And we call it the ion product constant. Okay, ion product because we're multiplying the concentration of 2 ions here. So that's Kw. Okay, questions on what we just did. Remember here, if you're like, I'm so confused right now, I'm so lost. Chapter 10 is not simple. This is a complex chapter, and this is going to be a lot of math. Okay, so definitely practicing will be important, practicing the homework problems, but be gracious with yourself here. And if you have questions in these next couple slides, please stop me. Please tell me to slow down, whatever. We're building up to understand pH. We just have to understand what water does first. So if we just recap, we have an expression for Ka and Kw. How are these different?
Kw is specific to water?
Yes, so this is just for pure water. And Ka is just for weak acids. All right. Ka, if you remember, is going to be the concentration of H3O plus times the concentration of the conjugate base divided by the concentration of the weak acid. And this is generalized. That's why it's just A minus, and HA. You could plug in any acid there, HCl, any weak acid, acetic acid. You could go look at the table. Any weak acid on that big table from earlier, you could plug in to this equation. And also, I want to remind you of something. This is synonymous with this. Remember, we said H3O plus and H plus are the same thing here. So if I wrote this equation with just H plus instead of H3O plus, don't be alarmed by that. They're the same thing. If I say, what's the concentration of H3O plus, or what's the concentration of hydrogen ion, those are synonymous. But Kw is no denominator. You just have H3O plus and OH minus, okay? So they're similar in the fact that they're both equilibrium expressions, but they're different because they apply to different substances. All right, so let's hone in a little bit more on Kw. There's a value for this. Okay, remember these numbers are constant and they're unique to their substance. So Ka is the same for, it's unique to whatever weak acid you're talking about. Kw is specific for water, and the value at 25 degrees is 1 times 10 to the minus 14. I told you it was very, very, very small. Do you guys remember that color-coded arrow, the purple, green, blue, orange arrow from chapter 7 when we talked about equilibrium? Barely, somewhat. If you go back and look at that slide from chapter 7, I wish I had it here in this lecture, but I don't. It reminds you that if you have a really, really, really small K, then the reverse reaction is favored, and you have mostly all reactants here. And this is a really teeny tiny K. So we mostly have water, but because we have a value for K, if we plug that into the equation now, what we have is 1 times 10 to the minus 14 equals the concentration of H3O plus and OH minus, okay? You can always plug in this value for Kw. That is Kw. And it's unitless. K equilibrium constants are unitless, no units here. Someone better say amen to that, right? Oh, Angelina, can you go back and explain that one more time? I'm just seeing your comment in the chat. Which portion did you want me to re-explain? I don't know if this was just typed or was from earlier. The last slide, right up here. Okay. Okay, real quick recap. Ka is just for weak acids. Okay, remember you can always go look at the table and see if your acid is strong or weak. Kw is just for pure water. Pure water, nothing else is there. So Ka, when we have this is the weak acid plus water. What you get is H3O plus and A minus. So you put the products go on top and the reactants go on bottom, but we take water out. So that's how you end up with this equation right here. Kw is just for pure water, where we have H2O and one molecule acts as an acid, the other molecule acts as a base, and you get H3O plus and OH minus. So these are your products, but we essentially take water out of that equation too. So we just have the multiplication of these two concentrations of these ions. Okay. Is that good? Mm-hmm. Okay, going back to Kw, now that we have a value. In pure water, the concentration of H3O plus and OH minus are equal, okay? If you're thinking back on what I just wrote. Okay, if we're thinking about this, every time one water molecule trades a hydrogen ion to the other, you're going to make one of each. You can't make hydronium without also making hydroxide ion. So the concentrations are identical, okay? So if that's the case, we can essentially say, well, they're both X. We can plug in same variable for both. And now if you do that, you end up with 1 times 10 to the minus 14 essentially equals X squared, right? You can plug in X for both because their concentrations are identical. So we can actually solve what is the concentration of H3O plus and what is the concentration of OH minus in pure water. Well, you just take the square root of both sides and you find that 1 times 10 to the minus 7, here it's molarity because we do have units because we're now talking about a concentration of these ions, is going to be the concentration of H3O plus and separately the concentration of OH minus. They have the same value, 1 times 10 to the minus 7, which is still a really small number. That is 0.1234561 molar. Okay, so not very much of this is happening in solution. So we actually just answered this question. So what are the concentrations? Well, again, you plug in Kw, you can plug in X for these concentrations, take the square root, and that's how you get the concentration of H3O plus and OH minus. Okay, so we're going to do a few practice problems with Kw. All right, let's read this one. What are the concentrations of the hydrogen ions? This is also like saying hydronium, okay, because remember H plus is synonymous with H3O plus, and hydroxide ions, OH minus, in a 0.1 molar solution of HCl. We have a 0.1 molar solution of HCl. So how do we begin to solve this? Well, the first place to start, anytime you're given a chemical compound, in any problem with chapter 10, you need to ask yourself, is it an acid or base? Is it strong? Is it weak? So what do y'all think about HCl? Is it an acid or a base? Is it strong or is it weak? Zoe says it is a strong acid, and you are correct, Zoe. So it's a strong acid. And what do we know strong acids do? Do they completely or partially dissociate?
Completely.
Yes. So I'm going to draw a single arrow. Yep. Thank you, Ashlyn. Single arrow, and we're going to get H plus and Cl minus, our products. All right. So if we start out with 0.1 molar of that and none of these, that's our starting point. What's going to happen in the end? In the end, we'll have 0 of this, and we'll have 0.1 molar, 0.1 and 0.1 molar of that. Okay. So we actually just answered one of the questions. Concentration of H plus is equal to 0.1 molar. That's a concentration because it has units of, what does M stand for? M is molarity. What is molarity? Remember, molarity is moles per liter. This is concentration. So hydrogen ions, the concentration would be 0.1 molar. And we can only say this because it's a strong acid. If it were a weak acid, it's not that simple. And I'm going to post a video of how you would go about it with a weak acid. But we don't know we haven't answered the second part. What's the concentration of hydroxide? How could we do this? How could we find the concentration of hydroxide ions? Any ideas? Well, we're going to use Kw, practice problems with Kw. What is Kw again? We're going to use Kw. We know the value of Kw. How could we use Kw here? Think about it. Well, we should have the concentration of H plus times the concentration of OH minus. And guess what? We know 2 of these values now. Kw is 1 times 10 to the minus 14. And now we figured out H plus. It's 0.1 molar. Remember, Ks are always unitless. I know this is kind of weird. but you should always have units of molarity on your concentrations of your substances, like your different ions or acids or bases. So now we just cross divide, right? We have 1 times 10 to the minus 14 equals 0.1 molar times the concentration of OH minus. So, and if we're looking for this, we'll just divide by 0.1. That cancels here. So what do y'all get for your concentration of OH minus? You should get 1 times 10 to the negative 13. Questions on what we just did? The first thing we did was we looked at the acid and we said, okay, is it strong? Is it weak? Because it's strong, we could say it's going to completely disassociate. So I don't care if it's HCl or what it is. If it's a strong acid, you can write this kind of equation and you can automatically know your concentration of H+. And then from there, we just plug that into our equation for Kw, and we solve for OH minus. So if you know one of these, you know this one or this one, you can always find the concentration of the other. Let's do a similar problem, but now what if we have 0.1 molar NaOH? Actually, I'm gonna switch this up. I'm gonna change the numbers. You have to just feel like it. 0.25 molar NaOH. What kind of, we have a base here. What kind of base is it? It's the strongest base, right? OH minus is the strongest. So we can write the same kind of expression. What products will we get? It'll be complete dissociation. We will get Na plus and OH minus. So if we start out with 0.25 molar of that and none of this, when this is done, we'll have none of our reactants. We'll have all products. 0.25 molar sodium ions and 0.25 molar of hydroxide ions. And we just answered this part of the question. It'll be 0.25 molar. That is the concentration of OH minus. But we need to know what's our concentration of hydrogen ions. And you have practice problems like this on your Mastering Chem homework. Stuff just like this, okay? So come look at these slides if you get confused on how to do those. Now we just use Kw. Kw equals the concentration of H plus or H3O plus. Remember, you can write it either way. And OH minus. So now we're just going to plug our numbers in. 1 times 10 to the negative 14 equals H plus times 0.25 molar. And we will just cross divide. Boom. What do y'all get? I got 4 times 10 to the minus 14. Does that sound right? Okay. So that's even smaller. That's ridiculously small, but that's how you would do this, okay? All right, any questions on what we just did? Okay, we're almost to pH. Last thing we'll talk about with water is how to define a solution as acidic, basic, or neutral. And I mean, think about this from a health standpoint. Our bodies have, we have a blood pH, so we have to constantly maintain the pH of our blood, and we're going to spend all Thursday talking about blood pH and how we regulate that in our bodies. But we have cells too, and cells, it's important that they maintain a pretty consistent pH, okay? Inside the cell, outside the cell. And we have to know how to classify any kind of solution that we put into the body as acidic, basic, or neutral. We have stomach acid, okay? That's a whole separate area of, we know that's really acidic. We have some HCl there. But how do we classify something as acidic, basic, or neutral? This is the foundation of pH, okay? So if something, just going to read this. A solution is considered acidic, basic, or neutral based on these concentrations, okay? And remember, in pure water, we know their concentrations, okay? And what is the pH of pure water? Do we consider pure water to be acidic, basic, or neutral?
Is it
Pure water, what was that?
Is it neutral?
Pure water is neutral. So we can already fill this in. If the concentration of H plus is equal to 1 times 10 to the minus 7, and the concentration of OH minus is equal to 1 times 10 to the minus 7, that's a neutral solution. If it's acidic, that means you have more H plus. So we can simply say, the simplest way to define it is that our concentration of H plus must be greater than 1 times 10 to the minus 7, which means the concentration of OH minus is less than, wrong sign. Less than 1 times 10 to the minus 7. Because, think about this right here. Here's our equation. If this one goes up, then this one has to go down. Why? Because Kw is a constant, right? And if you're going to maintain a constant, if the concentration of H plus or H3 plus goes up, to maintain the constant, the concentration of OH minus inherently has to go down, and vice versa. So if this is greater than 1 times 10 to the minus 7, then OH minus has to be less than. And that's when you have an acidic solution. Okay, if something is basic, it's the opposite. Your concentration of H plus is smaller, less than 1 times 10 to the minus 7. And the concentration of OH minus is greater than 1 times 10 to the minus 7. And so that means we have more OH minus in things that are basic. Now, this right here is a headache. All these 10 to the minus 7s, I mean, it's hard to look at. So we're headed somewhere that's much more simple to understand for our brains. But the foundation of all that is indeed these concentrations. Okay. Now, always remember, if we know the concentration of one ion, be it H plus or OH minus, you can always find the concentration of the other by simply plugging into Kw. So using Kw. All right. Here's a question. Milk. Milk has a concentration of H plus. That's 4.5 times 10 to the minus 7. Would you classify milk as acidic, basic, or neutral? And then what is the concentration of OH minus? What do y'all think? Boy, y'all must be tired today. Got quiet. Hannah says basic. Well, let's look at this. 4.5 times 10 to the minus 7. Is this greater than, less than, or equal to 1 times 10 to the minus 7? because that's kind of our key number here. Greater than, yes, it's greater than. The exponent is the same, the base number is larger, so this is larger, not by much, but by a little bit. So because it's greater than, let's go up here. Remember, if H plus is greater than 1 times 10 to the minus 7, it's acidic, okay? So milk, we don't think of milk as acidic, but it is slightly acidic. So now what's the concentration of OH minus? How do we find that? We'll just use Kw, okay? So we know Kw is 1 times 10 to the minus 14. And that we're going to plug in concentration of H plus, which is right here, 4.5 times 10 to the minus 7 molar. And that is times OH minus. Now we're going to solve, divide both sides by 4.5 times 10 to the minus 7. Cancels here. And make sure when you put this in your calculator, you put this in parentheses. That's where people very commonly make mistakes on exams and things like that, is they forget to put parentheses, especially you have a multiplication sign right here. You've got to put it in parentheses. So what do you get when you do that? I'm watching the chat. I'm going to go ahead and try to solve it too. Y'all let me know what you get. Divided by 4.5 times 10 raised to the negative 7. Oh, my calculator did not give it to me in exponents. It's 1, 2, 3, 4, 5, 6, 7. Yeah, so I got 2.2 times 10 to the minus 8. Is that what y'all got? Okay. So that's the concentration of OH minus. Okay. Little brain break for just a second. We're getting close to the end of the semester. This is my favorite meme to show. Okay, so if you don't think it's funny, just laugh for me, because I think it's really funny. How many of you guys feel like this? Hopefully you've seen this before. It's not a new meme. It's kind of an old meme. This is how I feel. It's how I always feel as we approach the end of the semester. I started out really good. I wish I could draw. I can't draw at all. But my favorite part of this whole thing is just right there. At least we're still smiling, right? We're still smiling, okay? You can do this. Hang in there, even if you're only hanging in there by a little old stick leg, okay? So, all right. pH scale. We just did all of that to lead us here. That is so me right now. Mine seems more like a scribble from a toddler. Oh, yeah. Funny story, my 2-year-old. You realize how literal kids are. She loves to color. And one time she was trying to color on, like, she put her paper up on, like, our couch. And obviously we don't want her coloring on the couch. So my husband was like, hey, Finn, just color on the floor. So she literally takes her little markers and just starts coloring all over the floor. And we're like, no. And his grandparents were over, and his grandpa goes, you told her to. You told her to color on the floor. And I was like, you did actually tell her to color on the floor. So now we say, put your paper on the floor. All right. pH scale. So because all this exponent stuff is nuts, the pH scale is going to simplify this. Okay, the pH scale is nice whole numbers between 1 and 14. You can have decimals, but you don't deal with all these negative exponents. And the reason this is nice, it just becomes really awkward to use molarity. And I'm gonna prove that. Which one's larger? 1 times 10 to the minus 7 or 1 times 10 to the minus 8? Which number's larger? I mean, my head just kind of hurts looking at these numbers, right? Because you're thinking, okay, well, 7 is smaller than 8. But on the negative scale, a -8 is less than -7. Yeah, so this one is larger. But it's just weird. You have to like really think about it. So to simplify stuff and to have quick visuals, we're going to use the pH scale. So first off, let's define pH. What is P? P is it's a representative of a mathematical function. And that just sounded really technical. It just means the negative log. So take your calculator right now. If you have your phone, you might have to turn it sideways. So if you have your calculator, on your calculator, you should have a button, mine's right here, that says log on it. Okay, and hopefully you've used this before in a math class or something. Hopefully you've heard the term log before. It's just the negative log. So always make sure you punch in negative log. And it's the negative log of any concentration, any number we want to put in there. And so if we're finding P of H, which is actually technically the concentration of H plus, then what we are doing is we're going to take the negative log of the concentration of H plus. We're just going to apply that log function to this concentration, this variable. To give you an idea of how general this is, you can also have P of OH. Okay, we know that hydroxide and hydrogen are two important ions that we have been calculating the concentration of. So what would be the P of OH? What would be the definition of that? Could we do that for the problem we just did on the last slide? You talking about milk? If you wanted to find the pH of milk, yeah, you could do the negative log of this value. We're going to practice calculating this. P of OH would just be, by definition, the negative log of concentration of OH. Okay, so you can do it for anything. So let's actually practice doing this. What are the following concentrations of H plus? Are they acidic, basic, or neutral? For these right here, and what is the pH? So let's do the first one together. 1 times 10 to the minus 7. If that's our concentration for H plus, is this acidic, basic, or neutral? Neutral. Okay, it's neutral. And what is the pH? So all we're going to do is we are going to take the negative log of 1 times 10 to the negative 7. You just put that in your calculator, negative log of 1 times 10 to the negative 7, and you should get 7. Okay, so pH equals 7 here. All right, I want you to go ahead on your own, do the next two. Tell me if the solution is acidic, basic, or neutral, and then tell me the pH. All right, let's look at these two. If it's 1 times 10 to the minus 9, that is less than 1 times 10 to the minus 7. So if that's the concentration of H plus, this is going to be basic. When you do the negative log of 1 times 10 to the minus 9, what did you guys get? 9. All right, let's look at the last one. 1 times 10 to the minus 4. This is greater than 1 times 10 to the minus 7, so this is acidic. And when you do the negative log of 1 times 10 to the minus 4, what did you get? 4. Okay, so here pH equals 9, pH equals 4. Does anybody notice anything? Anybody notice something peculiar?
For the ones we did, it was basically the exponent, but in positive form.
There's a little pattern here, and the pattern is explained right down here. If your concentration of H plus, if the base number right here, if you'll notice all these base numbers right here are 1, then whatever your exponent is, pH is the absolute value of that exponent. It's not negative. You can't have a negative pH, but you just, if it's 10 to the minus y, pH is y. Okay. But if your base number is not 1, say it's 2.5 or 3.2 or whatever, then this trick does not apply. It's only if your base unit is a 1. All right. So here's the here's kind of a new abbreviated version. Instead of using all these concentrations, we can actually apply them to pH, but we can say an acidic solution is one where the pH is less than 7. A neutral solution is one where the pH is equal to 7. And a basic solution is one where the pH is greater than 7. Okay. Now the concentrations of H plus still stand. Okay. These still do define, these right here define acidity and basicity. But it's much easier, am I right, to determine if something is equal to, greater than, or less than 7 versus 1 times 10 to the minus 7. Now these figures show you quite a few things. In this first arrow right here, you've got the pH in the right-hand column, and you've got the concentration of H3O plus in the left-hand column. And it just shows you how those two things relate. And notice, I'm assuming that the base number here is 1 times 10, all the way down. You could write 1 times. So you just look at the exponent that matches up with your pH number. Okay. And then it gives you several different substances to show you how acidic or basic they are. All right. Notice as you go down, you become more acidic. So it's these lower pH values between 1 and 6 really that are acidic pH values. And then the numbers above 7 are where you become basic. The column over here on the right shows you how the concentration of OH minus and H plus are changing together. Remember, if one goes up, the other goes down. So if you have 10 to the minus 1, for example, is much, much larger than 10 to the minus 13. And notice on these exponents, guess what? They always add up to what? What do they always add up to? 13 and 1, 12 and 2, 11 and 3. They always add up to 14. Okay? So that's because if you remember from KW, I'm going to write KW up here. KW is 1 times 10 to the minus 14, and that always equals the concentration of OH minus times the concentration of H plus, okay? So those always add up to the minus 14. And then we also have another equation here that you may realize is, this will be handy, I think, as well. pH plus POH equals 14, okay? So whatever pH is and whatever POH is, those will always add up to 14. And we will use these equations a whole lot in the coming problems. So I'll probably supply these equations on your resources page as well for exam 4. All right, so we're almost done, but hang in there with me. We just got a few practice problems we're going to do, and that'll be it for today. Now, we've talked a whole lot about if your base number is 1. What if the base number is not 1? What if instead of 1 times 10 to the minus y, it's like 2, or again, 2.5 or 3? The simple answer, how do you solve for that? Just put it in your calculator. Okay, that's how you solve for that. So for example, what is the pH of 2.3 times 10 to the minus 6? If that's our concentration of H plus, we'll just do the negative log of 2.3 times 10 to the minus 6. What do you guys get? Somebody may need to mute there. Check and make sure you're muted.
That's annoying. Making money. I have $30 a month. I could be.
Okay, I think that took care of it. Thank you. Okay, we got pH equals 5.64. There you go. So, okay, moving on. All right, let's look at this question right here. I'm going to turn this sideways to make it a little bigger. What is the pH of a 1 times 10 to the minus 6 molar HCl solution? Is it acidic, basic, or neutral? So remember, this is a strong acid. That's always the first thing you got to ask yourself. And because it's a strong acid, it will completely disassociate. So I'm going to write the same equation we did earlier. We'll get H plus and Cl minus. And when we start out with 1 times 10 to the minus 6, none of these things. When it's done, we'll have 1 times 10 to the minus 6, 1 times 10 to the minus 6. None of our reactant left over. So, is this acidic, basic, or neutral? What do y'all think? Here is our concentration of H plus. Is this greater than, less than, or equal to 1 times 10 to the minus 7? Madison says it's basic. She changed her mind. She says acidic. Sarah says that's right. It's acidic. 1 times 10 to the minus 6 is greater than 1 times 10 to the minus 7. Okay, so this is acidic. And what's the pH? So to get pH, we'll just do negative log of that value. But remember, our base number is 1 here. So we have a, we don't have to do any math here. We can say pH is just going to be equal to 6 because our base number is 1. Okay, but what if it's not a base number 1? What is 4.5 times 10 to the minus 4? I'm not going to write out this equation like we did up here. This still applies to this second problem, but we can know because it's a strong acid that our concentration of H plus is just going to be equal to that. So it's going to be equal to 4.5 times 10 to the minus 4 because this is strong and it will completely disassociate into H plus and Cl minus. So this is our concentration. All we do to get pH is what? We do the negative log of 4.5 times 10 to the negative 4. Is it 3.35, Dakota? Is that what you got? Okay. So pH equals 3.35. So if I were to ask you, which solution is more acidic? Which solution is more corrosive? Which one would you tell me? Number 1 or number 2? 2. Yep. All right, now I'm asking you, what is the pH if we have a solution of KOH and the concentration of KOH is 1 times 10 to the minus 3? This is a strong base. How do I know that? I recognize the OH minus here. And you can, again, go look at that table. When you see OH, you know it's a strong base. So we're going to have KOH, write the dissociation reaction into K plus and OH minus. And if we have initial 1 times 10 to the minus 3, oh, we are almost out of time. This will be the last problem we work. 1 times 10 to the minus 3 is how much we'll end up with of our products. So guess what? That is the concentration of OH minus. But I want to know pH still. I don't have concentration of H plus. How do I get pH? There's a couple ways to go about it. You can use KW at this point. Remember, KW equals concentration of H plus times concentration of OH minus. So you could plug in KW and you can plug in your concentration of OH minus would go right here. And you can solve for H plus. Then what do you do with H plus? You would take the negative log of the concentration of H plus and get pH that way. Or I think it's more simple if you take the negative log of OH minus, which is just the negative log of 1 times 10 to the minus 3. And what do you get? You'll get 3. What does this equal? This equals POH. And remember that 14 equals pH plus POH. So what we have is 14 equals pH plus 3. So you just subtract off 3 and you find that pH is 11. So you can do it either way. You can use POH and pH equals 14, or you can use KW. Your choice, whichever way you like. Questions on what we just did?